The Webb telescope is observing light that has been traveling for over 13 billion years. Yet, because the universe has been expanding, the light has also stretched. For the most distant worlds, we are looking back in time, nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we refer to as the singularity. As of now, this is our understanding of the Big Bang theory. However, the James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us astounded. Prestigious physicist Brian Cox has proclaimed that the groundbreaking discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new celestial discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the distinguished NASA administrator James E. Webb, stands as a marvel of modern astronomical exploration. This telescope represents a significant technological leap forward from its predecessor, the Hubble Space Telescope. Resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its herald. It utilizes cutting-edge technology and a design optimized for studying the universe in remarkable detail. Unlike Hubble, the JWST delivers clear and sharp images of distant celestial bodies, operating primarily in the infrared spectrum. This unique feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from our view. With its giant 6.5-meter primary mirror, composed of 18 hexagonal segments, the JWST dwarfs Hubble's reflector in size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in sync with Earth, ensuring a stable and continuous view of the universe. Looking into the distant reaches of the universe is not just about exploring space, it is also a form of time travel. The JWST uses infrared instruments to observe celestial objects and events from billions of years ago. Due to the expansion of the universe, the light emitted by these objects experiences redshift, shifting from the visible spectrum to the infrared. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling scientists to study the birth of stars, examine galaxy formation, and analyze exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of galaxies at the edge of the observable universe. This finding challenges the validity of existing theories about cosmic evolution, prompting a reassessment of fundamental cosmological assumptions. To better understand how we arrived at this point, we must take a brief journey through the history of space exploration. Early civilizations, such as the Greeks and Chinese, laid the foundation for understanding planetary motion by observing celestial bodies. In the 17th century, Newton's laws provided a theoretical framework for space travel. In the early 20th century, Edwin Hubble, an influential astronomer, made groundbreaking discoveries in observational astronomy and cosmology. His observations revealed that distant nebulae were actually separate galaxies, far beyond the Milky Way, transforming our understanding of the universe's scale and expansion. Hubble's law, which he formulated, demonstrated that galaxies farther away were moving away at higher velocities, providing strong evidence for the expansion of the universe. The post-World War II era marked the beginning of the space race. The Soviet Union launched Sputnik in 1957, the first artificial satellite to orbit Earth. In 1961, Yuri Gagarin became the first human in space, and in 1969, the Apollo 11 mission successfully landed astronauts on the Moon. Fast forward to 1990, when the Hubble Space Telescope was launched. It provided unprecedented clarity and stunning insights into the universe. The journey from ancient observations to the technological marvel of the James Webb Space Telescope showcases the continual evolution of our understanding of the cosmos. Hubble's discoveries helped reveal the vastness of space and reshaped fundamental ideas in astronomy. It captured iconic images, such as the Pillars of Creation in the Eagle Nebula, showcasing a stellar nursery formed by massive columns of gas and dust. Another milestone was the Hubble Deep Field, which captured thousands of galaxies in what seemed to be an empty region of space. The HST also studied exoplanet atmospheres, identifying components such as water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. By observing the supernova SN 1987A, it provided valuable insights into the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, captivating the world with its extraordinary astronomical discoveries. Its successor, the James Webb Space Telescope, was launched to build upon the technological advancements and lessons learned from Hubble. Today, our understanding of the universe's origins is explained by the prevailing Big Bang theory. Approximately 13.8 billion years ago, the universe began as a hot, dense singularity. It rapidly expanded, giving rise to matter, energy, and fundamental forces. As it continued to expand and cool, atoms, stars, galaxies, and cosmic structures formed. The Big Bang theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Though widely accepted today, the theory initially faced skepticism. Alternative models, such as the steady-state theory, proposed a universe without a specific beginning. Concerns about evidence supporting the singularity, expansion, and observed anomalies arose, but most objections were addressed over time. A pivotal breakthrough came in 1965 with the detection of cosmic microwave background radiation, aligning with Big Bang predictions. Space missions like COBE and WMAP, along with technological advancements, further confirmed the theory. Accurate measurements of cosmic microwave background radiation closely matched theoretical forecasts. Enter the James Webb Space Telescope. Equipped with advanced infrared instruments, it can peer through cosmic dust. Working primarily in the infrared spectrum, the JWST captures the oldest light in the universe, observing objects formed shortly after the Big Bang. Its infrared capabilities enable it to study star-forming regions, celestial nurseries, and the birth of stars hidden from optical telescopes. Since infrared light has longer wavelengths than visible light, it can penetrate interstellar dust, overcoming one of Hubble's limitations. The JWST can also detect cooler objects that emit primarily in infrared, making it ideal for studying exoplanets, brown dwarfs, and distant galaxies. As celestial bodies move away, their light waves stretch, shifting to longer wavelengths, redshift. The JWST's infrared sensitivity allows it to detect these signals, capturing light from the early universe and providing insights into its formation and evolution. One of its most astonishing revelations is the discovery of enormous masses of galaxies at the very edge of the observable universe. These ancient galaxies existed only a few 100 million years after the Big Bang, during the cosmic dawn. The mystery lies in how such vast structures formed so early in the universe's history. This discovery challenges our understanding of galaxy formation and evolution. The JWST's observations suggest that early galaxies evolved more rapidly and were more complex than previously thought. Some appear more developed than expected, prompting scientists to reconsider fundamental cosmological principles. Discrepancies between observed data and theoretical predictions have sparked intense debate within the scientific community. The unexpectedly large number of galaxies in the early universe suggests a more intricate and dynamic evolutionary process than existing models predict. These findings are not only answering long-standing questions but also raising new ones. The JWST's discoveries are forcing astronomers to refine existing theories, opening up new avenues for research that were once unimaginable. By studying the atmospheres of exoplanets, the JWST detects crucial chemical signatures such as water vapor, carbon dioxide, and methane, offering insights into potential habitability beyond Earth. Additionally, it is revolutionizing our understanding of star formation and black holes, unveiling new details about their influence on galactic evolution. As the James Webb Space Telescope, JWST, continues its celestial journey, it is not only unveiling secrets about the early universe but also challenging long-held theories about cosmic evolution. Each new discovery brings forth a wave of questions, pushing the boundaries of our understanding and forcing astronomers to rethink the very fabric of reality. One of the most perplexing revelations from the JWST involves the unexpected complexity of galaxies that formed just a few 100 million years after the Big Bang. According to existing models, such galaxies should be primitive, composed primarily of hydrogen and helium, with little to no heavy elements. However, spectral analysis from the JWST has detected traces of elements like oxygen, carbon, and even iron, elements that typically take billions of years to form through stellar fusion and supernova explosions. This raises an unsettling question. How could these early galaxies have matured so quickly? Could there be an unknown mechanism accelerating the formation of heavy elements, or does this suggest an entirely new model of cosmic evolution? Some scientists speculate that the universe may have undergone a more rapid and chaotic phase of star formation than previously thought, possibly driven by unknown forces or exotic physics beyond the standard model. The mystery of dark matter and dark energy. Another enigma that JWST is shedding light on involves dark matter and dark energy, two of the most elusive components of the universe. While dark matter is believed to provide the gravitational glue holding galaxies together, and dark energy is thought to drive the accelerated expansion of the cosmos, their true nature remains unknown. JWST's unprecedented ability to peer into the deep past has allowed scientists to study the distribution of dark matter in ancient galaxies with greater precision. Some preliminary findings hint at inconsistencies in how dark matter clusters, suggesting that our understanding of its behavior may be incomplete. Could there be a missing force or a new type of fundamental particle at play? Dark energy presents an even deeper puzzle. Observations from JWST indicate that the expansion of the universe may not be as uniform as previously believed. Certain regions appear to be expanding at different rates, leading some researchers to propose that dark energy might not be a constant force but instead a dynamic entity that evolves over time. If true, this would upend decades of cosmological theory and necessitate a radical rethinking of the universe's fate. A glimpse into alien worlds. Beyond its exploration of the distant past, JWST is also revolutionizing the study of exoplanets, planets orbiting stars beyond our solar system. Its ability to analyze planetary atmospheres with incredible precision has already yielded astonishing results. One of its most groundbreaking discoveries involves a planet roughly the size of Earth, located in the habitable zone of its star. Initial atmospheric analysis has detected traces of water vapor, methane, and even complex organic molecules. While this does not confirm the presence of life, it raises tantalizing possibilities about the conditions necessary for life beyond Earth. What if JWST eventually detects clear biosignatures, unmistakable signs of life? Such a discovery would not only be the greatest scientific breakthrough of our time, but would also redefine humanity's place in the cosmos. The future of cosmic exploration. The discoveries of the JWST are just the beginning. As the telescope continues to collect data, it is expected to raise new questions that will drive the next generation of space missions. Plans are already in motion for even more advanced telescopes, such as the proposed Habitable Worlds Observatory, which aims to directly image exoplanets and search for signs of extraterrestrial life. Meanwhile, theoretical physicists are scrambling to develop new models that can accommodate the JWST's unexpected findings. Could there be undiscovered laws of physics governing the universe's early history? Are we on the brink of a paradigm shift in cosmology? As we stand at the frontier of a new era in astronomy, one thing is certain: the universe still holds countless secrets, waiting to be uncovered. The James Webb Space Telescope is not just an instrument of discovery, it is a time machine, a storyteller, and perhaps the key to answering some of the most profound questions ever asked. The search for the first light. As the James Webb Space Telescope, JWST, continues its mission, one of its most ambitious goals is to detect the very first light that illuminated the universe, the moment when the cosmic darkness was shattered by the birth of the earliest stars. This period, known as the cosmic dawn, occurred when the first stars and galaxies ignited within the vast expanse of hydrogen gas left over from the Big Bang. JWST's powerful infrared capabilities have already allowed scientists to identify ancient galaxies dating back to just a few 100 million years after the Big Bang. But now, astronomers are pushing even further, searching for the very first population of stars, known as Population 3 stars. These stars, theorized to be massive, incredibly hot, and composed purely of hydrogen and helium, have never been directly observed. Recent spectroscopic data from JWST has hinted at the presence of these long-sought stars in the distant universe. If confirmed, this discovery would be groundbreaking, offering a direct glimpse into the processes that shaped the earliest structures of the cosmos. Understanding these stars could also unlock the mysteries of how heavier elements formed and spread across the universe, paving the way for the creation of planets and, eventually, life. The enigma of ancient supermassive black holes. While the search for first light continues, JWST has also uncovered a baffling cosmic mystery: the existence of supermassive black holes in the early universe. These colossal objects, millions or even billions of times the mass of our Sun, appear to have formed much earlier than previously believed. Standard cosmological models suggest that black holes grow over time as they consume gas, dust, and stars. However, JWST has detected evidence of fully formed supermassive black holes existing less than a billion years after the Big Bang, far too early according to current theories. This raises the question, how did these behemoths form so quickly? Some astronomers propose that instead of growing from smaller black holes, these giants may have formed through direct collapse, where massive clouds of gas collapsed directly into black holes without forming stars first. Others speculate that unknown physical processes, possibly involving exotic particles or new laws of physics, may have